Okay, so here's our next question, number 55. The open loop poles of a third order unity feedback system are at 0, -1 and -2. Let the frequency corresponding to the point where the root locus of the system transits to unstable region be k. Now suppose we introduce a 0 in the open loop transfer function at -3. While keeping all the earlier open loop poles intact, which one of the following is true about the point where the root locus of the modified system transits to unstable region? A. It corresponds to a frequency greater than k. B. It corresponds to a frequency less than k. C. It corresponds to a frequency k. And D. Root locus of modified system never transits to unstable region. Okay, so we have a lot of information given. Let's see if we can break it down and figure out what's the right option. So the question talks about root locus. So let's try and draw a rough diagram of the root locus plot of the transfer function when only the poles are given, and also when the 0 of -3 is introduced. So let's start by writing down. Okay, so we have been given the poles. The poles are at 0, -1 and -2. Now you should know that the poles correspond to the factors that are in the denominator of the transfer function. So let's call this transfer function as T1. So T1 equals K divided by S, that's the first pole at 0, S plus 1, that's the second pole at -1, and S plus 2, that's the third pole at -2. So we have number of zeros as 0. Now in order to draw a rough root locus plot, there are a certain couple of things that we will have to note down. So let's do that. We have our transfer function, well and good. Okay, so now let's note down number of zeros. We see that here the number of zeros is 0. We don't have any factors in the numerator, so they are 0. The notation for zeros, the number of zeros is m. Next, number of poles. The number of poles is 3. So we have 3 poles, 0, -1 and -2. The notation is written as n. Now the next thing we have to do is find out the difference between them. So the thing we need to do next is n minus m. N minus m is 3 minus 0, which is 3. Now this is important because n minus n implies the number of lines that go into infinity. Implies the number of lines that go to or that leads to infinity. Okay, now the next step is to see from which point these lines go into infinity. So here we have 3 lines that go into infinity. Okay, so we need to figure out from where they start or from where they actually begin, at least maximum number of these lines. So we calculate something called centroid. You should be a little familiar with what a centroid is. So the centroid is written as the number of poles n minus the number of zeros m divided by, oh, that's the sum. I'm sorry. This is sum of poles and sum of zeros. Sum of poles and sum of zeros divided by n minus m. So the centroid C is the sum of poles. The sum of poles is 0, minus 1, minus 2, which is minus 3. Minus sum of zeros is 0 divided by n minus m, we found it to be 3. So minus 1, which means that the centroid is at the point minus 1 comma 0. Okay. Alright, now the lines that go off into infinity, there is a word for this. These are called the number of asymptotes. Okay. So let's call these asymptotes as Q. Alright, now I'll draw a rough diagram here of the root locus plot. Okay, we have our real axis, we have our imaginary axis. Okay, now we have been given 3 poles. Note that the poles must be denoted with an X mark, while 0 is denoted with a O or a circle mark. So here we have one pole at 0, one pole at minus 1, one pole at minus 2. Now our centroid is at minus 1 comma 0. So right at that point, at this pole here, is also our centroid. So we have 3 asymptotes, right? 3 lines that go off into infinity. So 3 Qs. These are called asymptotes. So in order to draw the asymptotes, we have to use the formula for angle. So from this point, we don't know in which direction or which way we have to draw the lines, right? So we use the formula for angle of asymptotes. Okay, the formula is theta is equal to 2q plus 1 by n minus m into pi. Here q, because we have 3 asymptotes here, we have 3 asymptotes, we have to take q 0, 1 and 2. So we have 3 asymptotes. So the values, you will have to start from 0. When q equals 0, when q equals 1, when q equals 2, find out what the angles are. Now I'll leave that substitution and solving to you. Okay, so the angles you get should be theta is equal to, for 0, when you substitute 0, you will get an angle of 60 degrees. When you substitute 1, you will get a value of 180 degrees. And when you substitute 2, you will get a value of 300 degrees. Now 300 degrees can also be written as minus 60. Okay, so our angles are 60, 180 and minus 60. So that means from this point, from the centroid 1, we have our first asymptote that goes off into 60 degrees. Our second infinite is 180 degrees, which is this line here, the horizontal real axis. And then we have minus 60 here. Okay, so these are our asymptotes. Now, the next step is to find out which portion of the real axis actually exists in the root locus plot. So in order to do that, we have to take a test point. You can take a test point and check on any portion of the real axis here. So let's start with any point that is here on this side. You can take minus 3, minus 4, whatever, doesn't matter. So I'm going to take minus 3. Okay, so from that point, look to the right. How many poles or zeros you find on the right, the sum of those, if they are odd, okay, odd number of zeros and poles, that part of the root locus is present in the plot. Okay, so let's note here, let's see, if I take minus 3 point, count how many poles and zeros are there here, 1, 2, 3. 3 is an odd number, therefore this portion here exists in the root locus. Okay, so this goes off into infinity. This goes to negative infinity. So this portion exists in the graph. Next, take a point anywhere between -2 and -1. Let's take even -2, that's fine. So if I take -2 as the test point, look to the right, we have only 2 poles here. 2 is an even number, which means that this portion does not exist in the root locus plot. Now let's take -1. To the right side of -1, we have only 1 pole. Now because we have just 1 pole, it means that this portion exists in the root locus plot. Now if I take point 0, to the right we have nothing. We have nothing at all, which means this entire portion, it does not exist in the root locus plot. So here we see that there is nothing on the right hand side of the imaginary axis. So this is our first case. Our first case when there are only 3 poles and there are no zeros. Now let's look at the second case. The second case, the question says that -3 is introduced as a 0 to the transfer function. So we'll note down the transfer function now. This is the second case. -3 is introduced as a 0, which means now the transfer function is t2, and we'll write it as k into s plus 3. Because it's a 0, it lies in the numerator, divided by s into s plus 1 into s plus 2. The poles remain the same, right? Okay. Now let's do the same thing what we did for the previous part. Okay, so we have zeros, -3, poles, 0, -1, -2. So this is, alright, number of zeros. Number of zeros corresponding to m is 1. Number of poles, n, 3. N minus m is 2. So these are the asymptotes q. Okay. Now where would the centroid be? The centroid is the sum of zeros, the sum of poles first. So the sum of poles is -3 minus the sum of zeros is 1 divided by 2. This gives us -4 by 2, which is -2. So the centroid is at the point -2, 0. All right. So we'll just note down. Here we have our real axis. Here we have our imaginary axis. We have 3 poles at 0, -1, -2. And we have a 0 at -3. Okay, so now let's find out which part of the root locus actually exists in the plot. The same method as we used in the previous case. Now, it's all right, I have not tried and worked out the angle for this case. We'll just figure out without that which portion of the real axis exists in the root locus plot. So if we take the test point as -3, and if we look towards the right, let's start with in fact -4. If we take a test point -4, there are 1, 2, 3, 4. 4 points. It's an even number, and because it's an even number, the part towards the infinity is not considered. It does not exist in the plot. Now we'll take the point -3. If we look to the right, we have 1, 2, 3 poles. 3 poles. So 3 is an odd number. Therefore, this portion here exists in the root locus plot. Now take the test point as -2. Towards the right we have only 2 poles, which means this portion does not exist in the plot. Take the point -1 as the test point. Towards the right we see that there is only 1 pole, and that's a odd number, which means this portion here exists in the plot. If we take the test point as the origin here, we see there is nothing on the right side, therefore that does not exist in the plot. And here again we see towards the right side of the imaginary axis, we find nothing at all. So if we look at our options here, the right side is the unstable region. So root locus of modified system never transits to unstable region. It does not go to the right hand side of the plane. Therefore, option D is the right answer. Well, this is the entire solution, and I hope this has helped.